For example, I have in the top left here, I'm investigating the limit of the absolute value of x over x. And if I try to just plug it in, which is always what I want to do, I'm gonna try to plug it in, I get the absolute value of 0 over 0, which is like 0 over 0. And I have no idea what that is. So just plugging it in reveals nothing useful. So what I'm going to do is I'm going to plot it. And now it's time for a little bit of instruction in your TI calculator, how to plot absolute value functions. So what we want to do is we want to plot this function. So in the y equals screen, we need to enter absolute value of x over x in the TI. And the absolute value function, you get that from the catalog. And that appears as second 0. So if you go second 0, so let's go to y equals, and let's go clear out whatever you have there. Let's go second catalog, and the top item happens to be abs because it sorts alphabetically. So that's awfully convenient. So we'll go abs of x, and then bail on that, and then go div x. And then I'm going to go zoom 6, and I'm going to plot it. And I hope you're doing this along with me, because I get a function that looks like, is that what you got too? I hope so. So this limit is two-sided because there's no symbol right here, which means that we need to consider what happens as we're getting closer and closer to x and walking along the function, and I get to a point where there's a gap here. So since there's a gap, the limit doesn't exist, because the two one-sided limits, though they exist independently, don't match. So this is a place where the calculator as a tool is incredibly helpful. And I basically always plot my functions. It's like it's my modus operandi. I want to play with this function now, and I want you to do it on your calculator also. So I'm going to go to y equals, and I'm going to enter in sine of 1 over x. And I'm going to go zoom 6. That's the standard window. And you should get something that looks approximately like, kind of unclear what's going on there. And I think many people at this point would be like, yeah, that limit exists and it's probably 0. But like, I'm feeling a little uncomfortable with my calculator drew around that point. So I'm gonna zoom in. So I'm gonna push zoom and do zoom fit, that's zoom 0, and it's gonna rescale the function vertically for me. And now I'll draw what I get. And again, I really want you to be doing this with me, because this is incredibly valuable experience. Oh, and oh no, this is looking really funky in here. This didn't resolve my questions at all. This is looking really, oh, I don't know. I'm not sure what's going on. I'm not clear on whether the limit exists or not yet. Let's zoom in. Let's change the window so that the x lim is between negative 0.1 and 0.1. So I'm going to go window, and I'm going to change x min to minus 0.1. I'm going to change my x max to 0.1. I'm going to regraph it. And if you do that along with me, we should get something that looks approximately like this. This isn't making the picture any clearer, is it? Like, this is this is still just like a total mess inside of here. And no matter how far I zoom in, this is going to be a problem. In here, the function sine of 1 over x is trying to take on all values inside of the interval from -1 to 1. So like that's pretty messed up. You know, like it's going as high as +1, as low as -1, and it's doing everything. I would encourage you change these and make these even smaller, right? Go to like 0.001 and make those be them, and you'll see that it's never going to clear up. This is just going to keep being problematic, and you can zoom in and zoom in and zoom in, and it doesn't clear up. That's a dead giveaway that this limit does not exist, because the function is trying to take on all values. And the limit is a unique value. Let's do one more. This is another one where I try to plug it in. I'm thinking about x over x. And I get 0 over 0. At which point I'm like, I don't know. So let's plot it. So let's go y equals, and let's plot, after clearing, x divided by x, and go zoom 6. And you should get a picture that looks like mine. It's kind of unclear what's going on there above x equals 0. But it looks like this. And as I approach x equals 0, I'm looking at inputs, I'm watching what happens up here on my function. And we find that they're going to the same place. And where are they going? What's that value? What's that height that they're going to? What's the value of this limit? Yeah, thank you very much. So this limit is well defined. Even though the function is 0 over 0, if I try to plug it in, this limit is well defined and it's equal to 1. So on this page, there are two different scenarios involving 0 over 0. In this one right here, I had 0 over 0, and it generated this behavior where I've got a jump. And in this one down here, it generates where like I've got a hole, but like I can still like just jump right over it, like skip right over it, no problem, the limit exists. So if you get 0 over 0, that doesn't answer the question about what the value of the limit is. We have to do more work. So if you get 0 over 0, do more work. All right, so let's move on. And I want to tell you about what's going on here. And what we're dancing around is the idea of continuous functions. I think of continuous functions as ones that can be drawn in one stroke. So something that looks like that, or something that looks like that, or something that looks like that, or that, or that, or that, or that. You know, all of those are continuous functions because I could draw them in one mark as I drew across the page. And in contrast, that is a discontinuous function. That is a discontinuous function. That one is a discontinuous function. So these three here are discontinuous functions, which I abbreviate as DIS, CTS. So CTS is what I call is how I write continuous, generally speaking, because it's so many fewer letters, and I'm less likely to misspell it. So the formal definition that we work with appears in this blue box right here. We say that a function is continuous at a point if this expression right here, if the two-sided limit exists, if the function value exists, and those two things are equal to each other. So let me break that down for you. So the two-sided limit exists. Of course, that implies the existence of the one-sided limits and that they're equal to each other also. The function value is defined. And furthermore, they're equal to each other. Looking at this one right here, it looks like the function fails to be defined at a point. But the function has to be defined at a point in order for it to be continuous. Looking at this one, the limit doesn't exist because the two one-sided limits disagree with each other, and that violates that one right there. And this one here suffers the same problem that the two-sided limit doesn't exist. So these three features here of this definition forbid all three of these scenarios. So what I'd like to do is I'd like to talk on the next slide about continuous functions and really think about what it means for a function to be continuous. So I'm going to start and I'm going to do these four scenarios with you. So I want to talk through this first one here, and I'm going to name this function. And I would like you to use all available tools. So bust out that calculator, think about what's going on with the operations needed to evaluate this function. I'm a big fan of plotting, so I'm going to go into my calculator and I'm going to go y equals. I'm going to plot it. 2x cubed minus 4. Zoom 6. Did you plot it? This function on my screen looks like about like that. This function is defined everywhere, right? Because like no matter what point I look at, if I approach from the left and the right, they always match. There are no holes, and it never like jumps or anything like that. So this function is continuous. Let's do the next one. So let's call this one g. Looking at this function, it's not a simple polynomial, so like something could be up. It's going to take deeper investigation. I'm going to use my calculator. So I'm going to go y equals, and I'm going to enter this in. 1 divided by x squared plus 1. I'm going to go zoom 6 and plot this. But I want to think about like what could possibly be going on about this function. Like, how could this possibly be discontinuous? Like, what part of the function do I need to pay attention to in order to answer this question? Well, I've got a numerator. The numerator's nice. That's just always 1. I've got a denominator. And so we need to look at the denominator. Did you get a plot of this function? For me, it looks like this. Does your plot look like that? Taking a look at the denominator of the function. X squared plus 1. Well, 1, that's always bigger than 0. And x squared, that's always at least 0. It can't possibly be negative unless x is complex, but that's another class. So that implies that 1 plus x squared is bigger than 0. So the denominator is never equal to 0, which means that this function here is always defined. If you got a plot that looks like this, if your plot looks like that, then you're incorrect and you're missing parentheses. So I want you to make sure that when you entered this, you entered it as 1 over x squared plus 1, that you actually got those parentheses. These parentheses are critically important to the calculator correctly processing it, because otherwise it parses it as 1 over x squared and then adds 1 to it, because remember PPMDAS. So the outcome of this, therefore, G is continuous. Let's do one more. Let's call this one H. I would encourage you to think about kind of what we did on the last one. Like, what did we think about? We thought about the numerator and the denominator. And the numerator is never really going to cause us problems. The problems always come from the denominator. So I want you to think about the denominator. Let's plot the function, shall we? Y equals, clear, open a paren, use those parens, 1 minus 2x divided by, open a paren. Make sure you get those parens because otherwise the calculator will plot exactly what you tell it to. Looks like it passes through the origin. That's what I got. Is that what you got? If you didn't check the way that you entered the function in your calculator, definitely a no. This is not continuous. Why? What do we see about the function that makes it not be continuous? Well, I've got those, right? I've got a vertical asymptote rocking here, right? And I've got two of them. I've got two vertical asymptotes, right? And the presence of even one vertical asymptote implies discontinuous. DISCTS. How do we know the locations of those vertical asymptotes? How do we find the locations of vertical asymptotes? Yeah. Yep, we're going to take that denominator and we're going to set that equal to 0. So I'm going to solve z squared minus z minus 6 equals 0. I'm going to factor that and I'm going to get z minus 3 times z plus 2 equals 0, which means that z equals 3 or z equals minus 2. So if you're approached with a rational function, because it's a ratio, right? Not because it's capable of engaging in discourse with us, because it's the ratio of two things. What we're going to do in order to investigate continuity is solve where the denominator is equal to 0. And because that yields to no real answers, no real solutions in this one, the function is continuous. So there's a big difference between this one and this one, and that's why I put them both on this slide. Let's do one more of these. I'm going to call this K. Thinking about this function, I've got polynomial up here. Polynomials are nice. And then I'm taking 10 to the, and that's pretty nice too. Let's take a look at a picture of this function. I'm going to go into y equals, clear this out, 10 to the x squared minus 2x graph. No apparent holes, nothing weird going on, no division by 0, right? No logs of negative numbers. This function's nice. This function is continuous. Yeah, this function is continuous.